So unfortunately, it looks like we have another long one. So it's going to be one module this week. I know it's already a little bit behind, but due to the length of it, as it is, I'm already recording this one a little late. I won't be able to do two this week. So let's move into creating two variable equations. So in this one, we're going to talk about the creating equations in two or more variables in a graph. So obviously two-dimensional graph, and display their relationship. So in this, we're going to be talking about several types of functions, linear and exponential functions, as well as quadratic, direct and inverse relations, types of equations. So there are quite a bit of equations. So the reason for the length of this is literally just because of how long and how many topics there are in this one. So let's get started with this. So Jessica sold this many copies of her book, 166 copies of her book. Each day after the book's release, the number of sales decreased. So this is because it's a percentage, we know this is a exponential decrease. And the way we usually do this is when we're talking about growth or decay, growth is 1 plus the decimal of the percentage. But since we're dealing with decay, this is going to be 1 minus. So we're going to do 1 minus 0.17. So our growth factor, or in this case, our decay factor, is 0.83. So 0.83 is our decay factor. And when we're dealing with exponentials, the form is always our starting point, our growth factor, and then our exponent by whatever rate we're decreasing. So in this case, our starting point, our A as it were, our A would be how many sales it was as soon as it started. And then our B, let me do that in green, our B would be our 1 minus that, which ends up being this. So when we're starting this equation, we're going to start it at 166 parentheses 0.83 to the exponent of x, assuming that x represents the days after the, oh, actually it's saying t. So this is going to be t for the number of days sold. All right, going on here. It decreased. The number of sales decreased. I thought the function that represents the sales of the books after the release. So place sold that many copies each day after the book's release. Sales decrease. From my understanding, this should be an exponential decrease. I don't see why it wouldn't be. The day after a new book for a popular author was placed on the shelves, Jessica sold that many books. Okay, that's her starting point. Each day after the book sales, the number decreased by 17%. Uh huh. Okay. Uh, Write a function that represents the book's sales t days after its release. And I'm just gonna be it's Edmentum right now. I don't understand how else we can set this up. Let's try a multiplication sign. I don't know if it's going to be that picky. All right, well, let's see the correct answer. I forgot a zero. All right, so don't forget your zero, apparently, or Edmentum's going to be very upset at you. That's weird. All right, so 0.83, not 0.83. I'm not sure why Edmentum is that picky, but oh well. So Jessica's saving to purchase a new sign for her store. She already has this much. She adds that much to her savings account each time. Uh, the store sells 100 books. Create a function where X represents the terms that she sells 100 books. So this is a linear function. You can tell because the rate is constant. It's not changing. The rate at which this is changing. So in other words, this is going to be our starting point, our B, and the rate of change is going to be our M. So when we're doing this, we want to write this down as y equals 20x plus that plus 120, which is our starting point. So when we start this off, we're going to grab a line. We're going to start off at 120 and we're going to go up 20 over 1. And notice that these go up by 20. So we can see that that's our graph. I'm surprised it didn't get all picky, like, oh, you should have done array. Well, I guess it doesn't give us array, but there we go. I'm sure Nelson will probably find some meme about me versus Edmentum. And now we can see our introduction. So, as always, guys, watch the introduction. It does help, especially if you're having troubles with some relationships, like, for example, exponentials give students a lot of trouble, and knowing the difference between a linear function and exponential uh, are something you definitely want to look at. So, linear functions. So, this is just giving an example of a linear function. So, remember, linear functions have a constant rate. You can see that. Oh, and I almost forgot. I've been trying to show everyone nowadays. So, looking at projectile motion, just so you know, this is a quadratic. So, this is a good way of kind of seeing this. Um, so, whenever you're doing this in the scientific way, you're doing it by meters per second. So this number right here is gravity. This number right here is gravity feet per second squared. So the force of gravity going down on you. And this is if we're dealing with a ball that's thrown. So this might help you with some of them in case you need a review. And as always, guys, I cannot recommend enough the guided notes. It's going to help you. For example, this one helps finding exponential values and things like that. I always say it's old over new, but these will probably help you out a lot if you're having trouble with these functions. Let's get back into this. But those are always resources you want to look at. So linear equations just mean that there's a constant rate of change. They like use proportional. Um, and exponential means we're going to keep multiplying it at a constant percentage rate. So it is constant, but it's a percentage rate. That percentage is keeps continuing. So let's take a look at this one. We're looking at perpendicular lines. We're talking about lines that you're going to flip it. Your slope is essentially negative one over the other. So it's flipped. So, for example, if you have a slope of 2/3, the perpendicular slope is negative 3 over 2. So these so far have just been review of previous lessons. Let's move on. So here is the point slope form. So this is a good way to plug in a point and plug in your slope and then just calculate to get into y-intercept form. Sorry, there's a lot to cover, so I apologize if I'm going really fast. And you can always use a graphing tool um, when you're making these types of graph. Edmentum actually has them right here. There's a graphing tool right here in case you ever need it. I use Desmos because unfortunately Edmentum doesn't let you use the graphing tools when you need them. I don't even think it lets you use the calculator when you need it on the test. So being familiar with Desmos is going to be a good companion resource. All right, so here we're just talking about slopes, and if we want to find a line perpendicular to something else and including those points, we can use a point slope form. So with exponentials, if we're dealing with a decay, we're dealing with a number between 0 and 1, a fraction basically. If it's a growth, it's going to be bigger than 1. So that's where you get that 1 plus r that I mentioned earlier. We're going to multiply by or we're going to add it. If it's a decay, we're going to do 1 minus r. Do they mention it here? They do not. They should, but they don't. So we'll go here. I think they mentioned really briefly that you could have your exponent as a negative to make it a fraction, but usually I like the 1 minus r. So finding r, usually what we do is, this is an interesting way to find r. I always did it as new over old. What they're doing is they're doing the difference divided by that, and that'll give you this. So basically, what it is, it's new minus old divided by the original, and this will give you the change in R. I mean, it's useful, but I kind of like doing new over old, and then you're gonna add that. So to me, new over old is a little more useful because, okay, so let's see, you have this. You have this point 0.8. If you do the new over old way, we'll do the 1000 divided by 1. Still get the same number that they're getting. So I feel like doing this is more work because it's like, okay, you do this, minus that, you get a fraction, and then you're like, okay, cool. So now you have to add it to 1, and it's like if you just did new over old, you got this number right off the bat. So I think that's a little easier than doing this. Always do it as new over old. So y2 is our new number, y1 was our original number. And then in order to find your starting point, what you do is you just have the 0 value, and that'll give you your starting point. So moving on into actual exponents. I'm sorry if I'm going fast, and I'm going to keep apologizing, but let's say we're doing this. All right, so we're going to do the new over old. That gave us this percentage. It might be off by like a little bit because of how different they're doing it, but it's honestly not going to make too big of a difference because of round off. For example, if we're dealing with pandas, in this case, we can't have a fraction of a panda. So this tiny little difference, like I got 8.333, that's not going to make it that big of a difference. So we can use the graphing tool to predict how far in advance. So it's 19 years away, so they're just plugging in 19 and do that. And we can use this a graphing tool to solve this. So I'm not going to use their graphing tool because I really like Desmos. So here we're going to go to Math Tools, Graphing Calculator. And I'm going to do y equals 1,000. 3, and exponent x, and we're going to zoom out a lot, and we're going to see 19. So what we're going to want to do is each one of these squares, so this is 20, so 19 is right around here. And we want to get as close as possible to 19, so I'm scrolling up, and you see that, oh, I had it exactly. You see that it is just off by like a little bit, but we still got the same number. They got 38, so like I said, it can make a difference sometimes, but for the most part, you'll be fine. And during the test, I would look them over and I would see that you're off by 1, and I'm like, full credit, round off error. round off error happens, especially with exponents. So they're just showing you the data and how we would find it here. So we would go to 19 and find the data. All right, so let's find this. So basketball player, his height is this much, and then the first bounce, so it's going to keep decreasing. So our new is 4 and our old was 16. So we started off at 16 and then we went to 4. So this reduces to 1/4. So if our initial height was 5.5 and then, oh, almost forgot, we're dealing with inches. So we want this rate. Oh, wait, rate doesn't matter. Our units don't matter because our rate is still 1/4. So the first bounce is approximately that much. Second bounce is that much. What exponential factor? So we have that 1/4, and we want to convert this to inches. So that would matter. Our initial thing has to be in inches. So what I'm going to do here is grab this calculator. 12 times 5.5, and we have 66. That's 66, and we're decreasing by a rate of 1/4. So 66 and 1/4. Again, if you would have done it the other way, it would have been something like 16 minus 4 over 16. You get 1. Well, if you get 3 over 4, and then you still have to do the 1 minus 3/4. Always remember new over old. It's the easiest way to do this. I don't know why Edmentum gives you that really complicated way of doing it. So we get that. Moving on to the next one. All right, so going on to quadratic equations. So quadratic equations, they have their standard form. So the parent graph is x squared. If you make something negative, it's going to flip over. This isn't exactly that because it would be more down here. I'm not sure why they're making it go up. That's actually very inaccurate. This is a pretty bad graph because it should be down here. And it would be very skinny. So I think they're just kind of giving you a rough example of these. But Pythagorean theorem, for example, we use Pythagorean theorem to use. So square roots, we're basically using squares. Quadratics are just squares. And they're used a lot when we're talking about gravity and the force of gravity. So suppose Grandpa has a shiny new car. So this is his car in 1991. The lowest value, the car was at its lowest value of 500. Then it gained popularity amongst collectors. So basically, this was at $3,000. Then it went down to 500, and then as it gets older, it starts going up in value. We want to create an equation, so we kind of want to create a parabola. It's what it's telling us. So it's like the parabola provided gives us 3 distinct points. So we're going to make a parabola with 3 distinct points. So let's get into the actual problem itself. So when we're dealing with a parabola, we want to start off with our constant. So this is our constant where we started off. When x equals 0, basically when this was brand new, this was our constant. All right. And then we're going to need our vertex. Our vertex in this case would be the lowest point because we've already established that this went down and then back up. So we'll see how we involve vertex in a second here. So what we're doing here is we're plugging in the lowest point and x. So how long did it take for it to reach the lowest point? 12 years for it to get to the lowest point. This gets us to the point where we're solving an AB. So this is unfortunately one of the toughest ways to do this. I'm actually curious as to how I'm going to ask the Kahoot questions for this. But what we're essentially doing is we plug this in. This gives us the formula. Um, this equals that. And then we're going to substitute in. I don't know why we're plugging in this point. Let me see why we're plugging in this point. Using the XY charts, we then use the points. Okay, that made sense. And that we can create two linear functions, a and b unknowns. Oh, I see. This is um, what the newest high point. So using the newest high point, we have these two functions here. So we're graphing 2 points in the graph. We know this was the lowest point, and then we had another point here. So that's where we have this. Now we have this system of equations. Now we can solve for A and B. So remember how we did elimination a while ago? Oh, that probably, honestly, that might be an Algebra 1 topic. So if you guys need help learning eliminations or substitutions, let me know because you will need it for this class. So now using this, we're going to try to solve by substitution, it looks like. So we solve for B. Now that we have B, we're probably going to plug this B into one of these other formulas. So if we did this, we use this formula, which is the top formula. Now that we solve for B, we have to plug this B into the second formula. That way we're combining both formulas together. So then we plug that in there, and we're able to solve for A. So this is gonna take up quite a bit of time when we do this on our own. Now that we have B, now that we have A, we can plug this A into either one of these equations. So in order to find this quadratic equation with having 3 points, we're gonna have to use linear equations in order to solve for it. So moving on into this. So we're going to substitute those in, and now we have our parabola. And our parabola will include all the points that we talked about. The high point, the low point, and the point that it was, what was it, like 16 years later? Oops. Give me a second here. 38 years later, once it became a classic. All right, and another way of using parabolas, one that I'm a little more familiar with, you guys might be familiar with it if you ever take physics. This is you'll see parabolas a lot in physics. You usually talk about projectiles, and this is where I said that one. Oops, I don't have it open anymore. That one sign up thing will help you up. That one form. So moving into this, we're going to be doing rate of acceleration. So that could happen in feet or it could happen in meters per second. I don't know why they changed it. It was 16. Why are we talking about 32 now? Usually, yeah, see, feet thrown. Weird. They're saying 32 here, but they're saying 16 here. Huh. And then here. Is this just cut in half? Yeah, it looks like they're just cutting it in half. Huh, that's really weird. Okay. Apparently, oh, I see, because of the one half. When an object is thrown, propelled the other way, the object of the initial velocity, in contrast, has no initial velocity. In general, the equation is simplified to this. So we're cutting the rate of acceleration in half. So that's what happens when we throw something up or down. it's gonna cut the acceleration in half. Okay, that makes more sense. So general propulsion, yeah, cutting it in half. Okay, moving on here. So here's our equation. So someone's hitting the ball and it's going up. So next velocity. So this is the velocity and this is the height at which it starts. So the initial height, h naught, it's little zero, is known as naught. It's the position, so how high it's being hit up from. The velocity is how hard it's being hit. And this is just the rate of gravity cut in half. All right, so here's our equation. So that's how fast it's going. That's the initial position. And we'll be able, so you can see here it starts at 3 feet-ish. It goes up, 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 and gravity is slowly slowing this ball down till it gets to its maximum. And it's just going to start going down faster and faster and faster. All right, so let's take a look at our equation. So we're going to start matching up these ideas together. So Dwayne throws a ball with initial velocity. So remember B, when we're dealing with these, our A is our acceleration cut in half. That's a terrible color. It's way too bright. Our B is our velocity, and our C is our initial height. So let's take a look at these. So we're hitting the ball. He's throwing the ball up. So this is the initial velocity. So we're looking for something at 72. How high off the ground is he? 5 feet. So we're looking at this one. He's 5 feet off the ground with that velocity. Let's take a look at this. A watermelon is thrown 5 feet. So there's no velocity. There's no B. It's not being thrown up. It's just dropped, it looks like. So it's just being dropped from 5 feet. So we're dealing with this one. It has an initial height, but no initial velocity. Marcel shoots a foam dart. She holds the gun dart up. So we're dealing with meters per second. So we're definitely going to be looking at one of these three. Her initial height is 1.5, so we're looking at either these two. Does it have an initial velocity? It does, 73. So that means it has to be this one. Let's take a look at this other one. George drops it from 1.5 meters. No initial velocity, so no B. So it has to be this one because it's 1.5 meters above the water with no initial velocity. And you can always read these if I explain this way too fast. All right, direct and inverse variation. So direct variation, and I apologize if I'm going fast in the sense I'm missing content because the algebra class just finished something similar to this not so long ago. Direct variation is kind of like a linear function, except there's no b. Inverse variation is this idea that when the x goes up, the k goes down. So we're going to be dividing. So this one we're multiplying. As this x gets bigger, so is this y. Inverse variation is as the x gets bigger, the y is going to be smaller. So let's take a look and see what that looks like. All right, so here's direct variation. One gets bigger, the other one happens. And I just realized, I was realizing as I was writing it too, I was like, wait, I think it's, yep. This makes sense because as the k gets bigger, the y is going to get smaller because as we're as like let's say this is a million, so like let's pretend k is 2 2 over a million. It's a really teeny tiny little number. So the way I wrote it before didn't make any sense. Like as I was writing it, I was like, wait a minute, that doesn't make sense. They're still going to have a direct variation. It's just that our K looks different. So, whoops. At least, like, I was about to realize it and they pointed out right away. So, an inverse variation kind of does this, like, decay type look to it. It's a mirror image of itself almost. All right, so let's take a look. So, direct variation, like I said before, it's pretty much a linear function except our b is 0. It's literally the difference. So, so if something varies directly, it's going to have this constant rate that's always multiplied by. So if we're looking at this, we're going to see that k is equal. So we can solve for k by literally knowing these two numbers. All right, let's get into practice for it. So, and again, at 0, there's no b. All right, so here we're going to look at, so we want to figure this out. So total cost of admissions to circus A. So we're trying to find admission. Varies directly with the tickets. T. So we're trying to find this equation of, let me make it really dark. A equals KT. And our T, so our tickets is 3, and the admission costs is, and this makes sense. This is a great example of direct variation. Obviously, the admission is going to go up. The K in this case is the cost of the tickets. So, in order to do this, we would have this set up as 105 equals K times 3. So, we're going to do 105 divided by 3. To save time, I'm just going to use their calculator, although I hate what it does with my symbols. This 105 divided by 3, 35. So in other words, we're going to have A equals 35T. Every ticket costs $35. All right, so let's get into inverse variation. So inverse variation is when something is increasing, the other one decreases. So in this case, what they're saying is, I think this is speed. Yeah. So as the speed of something increases, the time it takes to get somewhere decreases. And that makes sense. The faster you're going, the less time it takes you to get somewhere. So that's where this time is equal to 50 divided by r, the rate of speed. So I believe in this case, 50 is how many miles per hour. It would take 1 hour. So the slower you go, obviously, the longer it would take. So let's get into an actual speed equation. They're still talking about this. So obviously, if you're going if it takes you 1 hour, you're going 50 miles. If it takes you 2 hours, you're going 25. If it takes you 5 hours, you're going 10 miles an hour. And we can always graph this. I'm just going to skip over that because I know this is a long thing. Quadrant 3 is a possibility, but it is not viable because there is negative time. It's in the past, but in practicality, we're measuring from now into the future. So usually we don't doesn't apply to the relationship we're examining because negative time. So open a graphing tool again. I'm not going to do that because they kind of graphed it for us here, and we're going to be dealing with inverse speed. So let's kind of talk about this. So inverse. So if we look at this is an inverse because it is y equals 2 divided by x. So I'm going to move this to the inverse part. I'm going to clear this out here. And we're looking at this 2, this one. So if we multiply r by both sides, q is equal to 2/5 times r. So this is a direct variation. It kind of looks like an inverse variation because it's a fraction, but nonetheless, it's still direct. As our r gets bigger, our q gets bigger. Not as fast, but it is still a direct variation. It's still a linear type of variation. This one, in order to get for a or b, you have to divide one of them. So you're going to get that in the denominator, because what will happen here is ab. So if we want to solve for a, we have to divide by b. And if we divide by b, it's going to end up being here. So this is an inverse variation. All right. And this one, notice how 1 over m, that's an inverse variation because 1 times 7, because this could be, just to make this a little more visual, be 7 over 1. So we have 7 over m equals n. So that's an inverse variation. This one we have on both sides, so if we multiply by 5, even though our slope is negative, we have a equals negative 5b, it's still a direct variation. It's just our slope's negative. So this is going to be a direct variation. And this one is neither because we're not multiplying by anything. In other words, this is a linear function. This right here is our y-intercept. This is our y-intercept. So this is neither. It's not direct nor inverse. It's a linear function. All right. Hopefully you guys can fast forward through the parts that you already know. Moving on to the next one. Now we're going to talk about other types of equations. And then we're finally going to get to that activity. All right, so going into these, see other types of equations. I might honestly save the activity for the end. So we can model the path of a roller coaster, weather patterns, and production. So this is just some polynomial that we see here that causes different waves to happen. So when we're doing this, when algebraically, so when dealing with volume, we're dealing with length times width times height. So Casey's building a flower bed in a prism. She wants the height to be 13 inches shorter than the width. So usually when I hear these, I go height equals width minus 13. And she wants the length of the flower bed to be 24 inches longer than the width. So L equals width plus 24. And this will allow us to make a polynomial where we get this length times width times height. That's our length times our width times our height. And we'll probably see this in the next one. Oh, there we go. They're already doing it for us. And that's our length. All right, and then length times width times height is going to give us this polynomial after foiling everything. So distributing, then we foil. So you can box method this if you want. And then let's say we want the width to be 5 inches. We plug this in. That'll give us the volume. And we see that this isn't possible. So you're going to have to make something bigger than 5 inches. The width can't be 5 inches. because obviously, well, for example, let's think about it logically. If you want the height to be 13 inches shorter, you would have a negative height, and you can't have that. So obviously, you have to have at least 14 inches for this to work. All right, so let's take a look at this. So Ricardo is building a box. He wants to be uh, the box be 13 inches longer than the width. Okay, so length equals width plus 30 inches. He also needs the height to be shorter, so the height has to be the width minus 5 inches. So when we do this, let me do this. I'm going to distribute, so I get y minus 5w. And I'm going to FOIL this. Usually I like you doing the box method, but I'll FOIL this one. So first, outer, inner, and last. So our first one, I don't like how close those colors are to each other. W cubed, inner would be plus 30w squared. Uh, inner, a little bluish, is negative 5w squared. And last, I'm going to make it more pink to make it different. Negative 150w. So the middle ones are going to combine. I could have done this with box method, but just so you guys get more practice, those middle numbers combine. I'm just going to bring everything down. So this ends up being our equation. So the first one is going to be, oh, and they're using x instead of w. So this is going to be x squared, and then it's going to be 25x, oh, cubed, sorry, 25x squared, and negative 150. Uh, is possible for the width to be, we want it to be bigger than 5. So it's not this. I'm going to say this just to do this. I'm not going to plug it in. I think these two are way too big. Well, first of all, it's between this. Obviously can't be 0.48 because we have to make it bigger. So the units are actually giving this away. And there you go. Like I said, the easiest way to solve that was this can't be a negative number because it would make everything a negative area. Volume, sorry. Negative volume. All right, so moving on. So rational equations are when we essentially have an x at the bottom. It's very similar to indirect variation. And that's because indirect variation looks something like this, where we had the x at the bottom, but a k. Rationals are the same idea. We're dividing, so we get this. So rationals, we kind of already dealt with them. So when we're dealing with rational equations, expression with at least one rational expression. So in other words, we have x at the bottom. Easiest way to say it. Fraction with x at the bottom. So let's take a look at this. So production per day. So this is the hours. We're going to subtract 3x, non-defective refrigerators. And then we're finding the average. So this is a rationale behind this. Production hours per day. So this is how many fridges we have and how many defectives we have every hour. And then this is the average. So we're dividing it. So averages do cause this rational expression. All right, so let's see here. So Samantha, for each 8-hour shift, she earns this much plus for each item she's selling. All right, so Samantha 72 plus 10x for each item she's selling. Which expression describes the amount in terms of x? We're going to divide it by x because we're going to assume this is how much she gets, and this we're basing it off of how many items she's selling. So we have this expression here. Now, oh, okay, cool. I was a little worried that they might have us break this down into two different expressions because I saw this here, and I think they were probably going to try to trick me here. So that would be our expression because we're doing it based off items sold. So clear the board. Moving on to the next one. Probably seen situations involving distance and area modeled in radical equations. So radical equations is just talking about square roots, basically. A radical is a square root. So Steve wants to increase the area of the deck by 9 square feet. It makes sense that there's going to be a radical. Could we write an equation to figure out the length of that square? So we're talking about a square. That's why we're dealing with square roots. So area is equal to side squared. We kind of did this in the last module. So let's get into this. So in other words, the side is equal to the square root of the area. Obviously, that's how they cancel out. So if the original side is x, and what we're going to do here is we're going to do x squared, and we're going to add 9 feet to the area. That's where we get this. I feel like this one would have been useful for you guys in the last unit. I don't know why they didn't do it. All right, and this is how we can solve for the new side. All right, so let's get into this. So the old area, or the old side, was 6, and then we had the area, we added 9. So in other words, the new side has to be around 6.7. So adding that 9, we have to add point that 9 area, we have to add 0.7 in the length of the side. Let's say the original area was an 8 square feet. So by adding 9, that 8 turns into 8.5. So we're adding 0.5 to the side, to the new, so the new side is 8.5. All right, so Allison created a diagram of a fence. The new fence pen is this. Allison labeled the side length. So in other words, she's adding 12 to the area here, where X represents the original fence in area. What change in the expression happened? Okay, so she wants to increase the fence area by 12 feet. Oh, well, that was 12 square feet. This is an area. So remember, feet, when we're talking about area, the reason why it's square feet is like, let's say this was 12 square feet. It's literally 12 squares. That's where the expression 12 feet. Feet, it would be talking about the one dimensional thing here. So, for example, this would be 3 feet. This would be 4 feet. Inside here are 12 square feet. And that's roughly related to this, but not really. Let's go on. We could use radical expressions when we're dealing with cylinders. Cylinder is the same thing. We're going to be dealing with volume, but we're going to be talking about the radius, increasing the radius length. So a lot of times we're going to be dealing with radicals. It has to do with area, in other words. All right, let's do an actual graph on this. Okay, it's not as bad as I thought. I was debating on if I had to make another video for this one. So recall that we modeled using graphing tools. So this is going to be that flower bed one. Remember, the equation represents the volume of flower bed, so either it's width, length, or either. Use the pointer, the intercept. So we're going to use a graphing tool. I'm going to use Desmos just because I do not like the graphing tools that they have here. Copying and pasting it is going to cause some issues, and you'll see them right now. So you see here that it doesn't give you the exponents, but you can just do that by Shift 6. And apparently there was something in the way there. Okay, if I highlight it, it does the exponent. Okay, so we have this. I don't really need to put a Y. The reason for that is Desmos is automatically assuming you're doing a Y. So if I look at the x-intercepts here, I see that there is an x-intercept at negative 240. So when you're writing your equation, this would be x plus 2 or plus 24. And the other expression would be 0, 0. So this one is just our x. So this is probably our width. And then our final expression is 13. So it's always going to be the opposite. So this is x minus 13. So we can say here that we want the height to be about 24 inches bigger. I'm sorry, the length to be 24 inches bigger than the width, and we want the height to be 13 inches smaller. And so, position, so the fit sign of the x intercepts, we get the expression, I should say equation, because it is a y equals equation. Y equals x, x minus x plus 24. What is this asking? Use a pointer to find the x-intercept. So this is positive increases. Okay, cool. The height is 13 less than the width and the length. And I think they actually said this in the last thing. It's been a while since we've been in that slide, and the length is 24 inches longer than the width. All right, I'm going to submit that, and they show it right here. All right, so the answer, strict inequality. So if we're looking at this, obviously our length has to be bigger than 13. So we want it to be bigger than, can't really make it equal to 13. The reason for that is because it would have a zero height. So we're going to say strictly bigger than 13. Because otherwise we get a negative height. All right, so recall the expression. Blah, blah, blah. Now open the graphing tool and do this. Find the average effective rate of this. Okay, so we're going to use this expression. Again, I'm going to use Desmos because I do not like. I just feel Desmos has a lot more options than the graphing tool. But if you guys want to use the graphing tool and don't know how to access Desmos, you go here and go to graph. I like Desmos because Desmos lets me do stuff like this. I can do the divide symbol and it automatically gives me this division. Fraction, I should say. Division, fraction, same thing. 3x minus 3x. And we want to find the value of 15. So 15 per hour. Here's an x number of hours. Now open the graphing tool. Use the pointer to determine how many hours of production it would take the average effective. So y equals 15. I'm assuming that's what it means. So if we go to y equals 15, we're going to get about 10. Looks like 11. 11 or 10. We get a decimal, it looks like. An easy way to kind of solve this is you can make a table. So, table this. We have this equation, and if we're trying to make x equals 15, we can literally type in 15 here, and it'll give us the answer. Guess they want us to say 10. I'll open the graphing tool, use the point. Let me use their graphing tool. Maybe their graphing tool does have something useful here. Relationship. We're going to do a custom relationship. Y equals, I guess the equation editor makes it not that bad. X over X. And of course, it's going to give me a hard time. Oh my gosh. I'm going to say 10. So this gives me 10 when I plug it in for X. Oh, I was doing Y before, huh? Well, let's see. What if I put Y? Alright, so I'm going to say, according to the graphing tool, X is 15, Y is, if that was what they were referring to, 11-ish. Close enough. Oh, because we can't have a fraction of a defective fridge. Give myself a 4 on that one. The word was awkward. Alright. I mean, we still got it right, but still kind of weird. And then our summary, as always, guys, watch these videos, are complicated. Unfortunately, that quadratic one that I went over really fast is a big part of the test. I'll see if I can explain it a little bit better during the Kahoot. Alright, guys. So I know these have been long. Hopefully, once we do the next ones, they won't be as bad. Take care, guys.